Hi, welcome back to Derivability. I hope you've been watching some of the previous videos about rigid body motion in 3 dimensions. Okay, it takes a while to work through all the details here. So in this one, let's take a look at Euler's equations for axisymmetric bodies. Okay, that's going to involve something called Euler's angles. Okay, so let's suppose we have a coordinate system, capital XYZ, that's fixed in space, and we have a lowercase xyz coordinate system that's kind of attached to our rigid body. Okay, not exactly this time. So let's suppose the z-axis, lowercase z, remains along the symmetry axis of the body as it spins. And then let's suppose that this spin rotates around the capital z-axis at capital omega rate. Okay. Now in this case, 2 things. We have this capital omega, and there are times we set that equal to the spin rate, omega, little omega sub s, and we end up with what are called the Euler equations. Okay, and if we leave that different, the capital omega that is, then we end up with something called the modified Euler equations, which we'll be getting to soon. Okay, once we have those, then we can actually start talking about Euler's angles. Okay, so the net angular velocity, omega, lowercase, is the sum of these 2 angular velocities having to do with this body. Okay, now the thing that's different here than maybe we've seen before is that we can permit lowercase xy axes not to be fixed with respect to the body. Okay, of course you never have to require anything, but in the past it was helpful to do that so that we could define them as principal axes and make sure that the products of inertia of the rigid body, the spinning body, the products of inertia were 0. Okay, but as long as we leave the axis of symmetry attached to the body, that z-axis, and of course if that's axisymmetric body, then if that's a principal axis, then x and y will be 2 automatically, even if they move with respect to the body, okay, due to the axial symmetry, okay, which is kind of a nice feature of the axial symmetry. Okay, now if you're wondering what exactly is meant by an axisymmetric body, think of a volume of revolution. Okay, so if that makes sense, if you understand that, then you're understanding an axisymmetric body. Okay, now what I've done here is I've pasted in are basically the kind of the rotational version of Newton's second law, if you like, the sum of the moments. A here means either a fixed point or the center of mass, centroid. Okay, and what we're going to do is we're going to figure the rate of change of this angular momentum in the rotating frame, but then we have to figure its change due to the rotating frame. So that's where the cross product comes in. Okay, our angular momentum components. Okay, we've talked about these before if you've seen some other videos, but they're a little different than what you might encounter in 2 dimensions. Okay, and they in general involve our products of inertia. Okay, but due to the symmetry here, okay, the products of inertia are going to be equal to 0 due to the symmetry. Okay, in particular the axial symmetry. Okay, so what we get to do is we just get to we lose all these mixed subscript products of inertia. Okay, so it's greatly going to simplify our work. Okay, and then the remaining terms are going to feed in to this derivative term and also to that cross product. So let's see how that works out. Okay, so I wrote the cross product up at the top. You can set that up using the usual determinant approach. if you want to. Okay, I'm assuming you probably know how to do that, especially if you've seen a few of these other videos. Okay, and then the time rate of change of the angular momentum components, because the products of inertia go away. And then finally down at the bottom, basically, combining both of those, we get the sum of moments in each direction. Okay, the capital omegas there are, of course, the rotation of the reference frame in the fixed frame, the capital frame. Okay, and if you set capital omega equal to lowercase here, you actually get back to the standard Euler equations. Okay, also it should be pointed out that the lowercase omega in all of these formulas with the various components and so forth in these various places, the lowercase omega stands for the net angular velocity, okay, which is the sum of the two different angular velocities of the system, the spin and the rotation of the reference frame. Okay. All right, now with that, we're going to be ready very soon to start talking about the Euler angles. Okay, so hang on for that. All right, now for the definitions of the Euler angles, or Euler's angles. Okay, we often call these by the Greek letters psi, theta, and phi. Okay, now we can use the previous picture, although we have to put a few more constraints on this than we had before. Okay, we already decided that lowercase z was the symmetry axis of the axisymmetric body, the rigid body. Okay, now we're also going to insist that the lowercase x-axis does not need to coincide with any particular other axis, but it's always going to be in the capital XY plane. Okay, it's going to rotate around that horizontal plane. Okay, and what this means is that the y lowercase y direction just is what it is. Okay, so theta is the angle by which little z rotates away from capital Z. That's called the nutation angle. Okay, little x is always in the big XY plane. That angle is phi, measured from the capital X axis. That's called the precession angle. Okay, if we dot these, that is, take the derivative, time derivative, we get these rates of nutation and precession. And if it's helpful, we might call those omega subscript by the appropriate angle. And then the angle psi has a magnitude of omega sub s. Psi dot, we can say, is the rate of spin. That doesn't need to be measured from any specific position, just somewhere convenient around that lowercase z axis. Okay. Now, the first equation, otherwise, that I have in the typeset type, capital omega equals omega sub phi plus omega sub theta. Okay, that is not necessarily obvious from the picture. Okay, but the idea here is that these are just two different ways of talking about the rotation of the body in the capital XYZ system. Okay, before we were calling it capital omega, but now we can reparameterize that in terms of angles theta and phi. Okay, so that again, that's maybe more of a definition than anything that's intuitively obvious here, or obvious from the picture. Okay, then to get the net angular velocity, we take capital omega plus omega sub s, as we've discussed before. So it's the sum of these three omega vectors. Okay, and if you like this very last one here, we could write that as omega sub psi, if you like. Okay, so now let's see if we can figure out what the directions of these vectors are in terms of our ijk unit vectors, and the ijk unit vectors are going to refer to the rotating axes, the lowercase that I have drawn in the blue. Okay, so let's see if we can get that figured out. Okay, now two of these I think are pretty straightforward to try to understand. The third one might require a picture, okay, of the sort that you're probably accustomed to. Now, for omega sub s, let's just understand here that, basically it defines the z-axis. Okay, so omega sub s right here. Okay, so its rate psi dot times the k hat unit vector. Okay, now omega sub theta, okay, it's happening at a rate theta dot. Okay, and I'm going to claim that it rotates about this lowercase x axis. Okay, now that works, but only because lowercase x is always in that horizontal plane, the capital XY plane. Okay, otherwise it would be a little bit more messy. Okay, now the omega sub theta, okay, has a magnitude of, omega sub phi, down here at the bottom, that has a magnitude of phi dot, which I think we've already decided. Okay, but why the rest? Okay, well, first, notice that the rest is a unit vector. Okay, if you take the sum of the squares of the components there, you're going to get 1. Okay, there can be no I component, x component, because this is happening basically about the capital Z axis. Okay, because little x is always rotating in the capital XY plane. Okay, now as far as why it is that unit vector, I think might require a different picture. Okay, so let's take a look at that picture, and I think we'll be able to figure that part out. Okay, so let's take a look at this new picture that I've drawn. All right, and so omega sub phi points in the capital Z direction. So if you like, I've written that as phi dot and then times a capital K as a unit vector, as if that's the unit vector in the capital Z direction. Okay, now lowercase x axis is always perpendicular to the capital Z, so it's not in this picture. Okay, so anything that points in that capital Z direction is always going to be a linear combination of things that point in the lowercase y and z directions. Okay, so I think we can see here that when we create a right triangle to figure vector components, the component that points parallel to the little z-axis, phi dot cosine theta, then attach the k hat vector, and then this y component phi dot sine theta. Okay, so I think that's how we can figure out what omega sub phi is. Okay, now if we go back up, I'll just kind of scroll this back up here. Okay, if we go back to these definitions of capital omega and the net lowercase omega, okay, we can actually write those each in terms of these Euler angles. Okay, and commonly, because we have this sum here, commonly we just call that component omega sub z, just for short. Okay, but when you get down to business, you have to remember what that is really equal to. All right, so next what we can do is we can go back to those modified Euler equations from earlier in our video and actually plug in for omega x dot and the other two dots, and then lowercase and uppercase omega components. Okay, so let's take a look and see how that pans out. All right, so we're back to the modified Euler equations and what we figured out for the components of capital and lowercase omega. Now, because we have axial symmetry, we don't really need to worry about I sub x and I sub y. They're different in terms of spatial directions, but they have the same numerical values. Okay, so we can just call those both I. All right. Now, what we'll need to do is, for the first term in each of these three equations, we need to figure out what omega x, omega y, omega z dot are. Okay, well, omega x dot, Okay, well, omega x is just theta dot, so omega x dot is theta double dot. Okay, now omega y is phi dot sine theta. So if we take that derivative, we're going to use a product rule. We're going to get phi double dot sine theta plus phi dot theta dot cosine theta. All right. Now omega sub z, okay, is this whole thing here. And again, just for brevity, we're just going to leave that written as omega sub z and omega sub z dot. Okay. All right. Now, otherwise, what we need to do is we need to plug in, of course, each of these for the dots over here. Okay. But also, we need to kind of carefully plug in for omega, capital omega sub x, okay, capital omega sub y, and capital omega sub z appear in those positions. Okay, and then, you know, it's interesting to notice here that the lowercase omega is the same as the capital omega, except there's an extra term here. That is the psi dot. Okay, but all that said, we need to plug in for the lowercase omega sub x. Okay, the lowercase omega sub y, and now the lowercase omega sub z. Okay, looks like I underlined some things in the wrong color here. Excuse me. Get some of this fixed for us. Okay, color coding is supposed to help, right? Okay, so anyway, there, I think I got everything color coded correctly. All right, so I'm going to plug those in. Pause the video here. I'm going to paste those in. If you want to do some algebra, some substituting to see if you get the same thing as I do, maybe you can pause the video and check here in just a moment. Okay, so what I've done is I've substituted and, you know, did a couple of simplifying algebra steps. Of course, one of those is that I sub x and I sub y are equal, and we're just using I in various places here. Okay, so you can do some grouping. In that third equation, you get everything to cancel except for this first term, very interestingly. Okay, all right, so these are the most general version of Euler's equations that use the Euler angles. Okay, and again, it should be pointed out that these only work for the axisymmetric body. Okay, sometimes you'll hear books, authors, teachers talk about a symmetric top. Okay, as if we're talking about like a top, like a child's toy. Okay, very, very good physics there. All right, now there are some special cases. Okay, if this is the most general case, but there are some special cases that I'll show you on a clean board in just one moment. Okay, now you may know that one very common sort of case is the steady precession of a top or an axisymmetric body. Okay, now steady means that the rates are constant at the very least, and theta, the so-called nutation angle, just makes a constant angle between those two z-axes. So what happens here very, very nicely is that we just don't actually get any moments, at least net moments, about the y or z axes, that is the lowercase y or z axes. Okay, and the case for m sub x simplifies greatly. Okay, now what you may ponder now is another special case of this special case. Okay, so in addition, okay, what if the nutation angle is equal to 90 degrees? Okay, all right, well, in that case, we have sine theta equaling 1, cosine theta equaling 0. Okay, so that kills off our entire first term there. Okay, then if you go back and take a look at our definition for omega sub z previously, okay, then we get a very, very simple case of steady precession. All right, in that special case, of course, you still have the sum of moments in the x and y directions the y and z directions equaling 0. Okay, and then you get a very, very simple looking formula for the sum of moments in the x direction. Okay, that picture would have our symmetric object down here. Okay, and of course this would be our z direction now, lowercase z. Okay, this would be our lowercase x, and then our lowercase y would point straight up. Okay, that happens sometimes, especially in some homework problems. Okay, all right, well, I think that's going to do it for us for right now. Okay, hopefully this has been helpful, along with some of your other studies, to know how some of these things are derived or proved. Okay, thanks for hanging around here. If you like my content, please subscribe to the channel. Leave me a comment. I'd love to hear what you think about everything. And good luck in your studies, and we'll see you again soon on the channel.